So our final speaker in the morning session is Mark Bunn, and he's going to be speaking on Make Up Your Mind, the Price of Online Queries in Differential Privacy.
Okay, thank you for the introduction. Can you hear okay? Okay, so I'll be talking about theoretical work in differential privacy, trying to understand how changing the model of interaction can sometimes affect what kinds of tasks are compatible with the definition of differential privacy. And this is joint work with Thomas Stanke, who's a visitor here, and with John Ullman. All right, so in this talk we'll work in the usual model of privacy-preserving data analysis, where you have some collection of data, for instance, census data, biomedical data, or social network data. And for our purposes, we'll do the usual thing of abstracting this data as a data set, x1 through xn, where each row xi will correspond to one individual's data. And we're going to hide this data set behind this data curation mechanism, which we'll abbreviate by M for mechanism. And this curator M will facilitate a data analyst, pictured over here on the right, asking some sequence of statistical queries about the sensitive data set x1 through xn, and then receiving some sequence of answers that should represent the values of those queries on the data set. Okay? So I want to emphasize that this should be thought of as an interactive process. So a data analyst has some particular study that she wants to perform on the data set. And so she's not going to ask, every possible query one could ask about the data set, but has some specific sequence of queries in mind, and is going to interact with the mechanism in some way to answer those questions. Okay? Now, a natural question is, how exactly should we model this interaction? So there are a couple of natural choices for this. The first is sort of the ideal model of statistics, which we'll call the offline model, in which the analyst knows ahead of time, before looking at the data at all, what all of the queries she's ever going to ask are, and then asks them all together and receives her answers to those queries all at once. Another reasonable choice is what we call the adaptive model. And this probably more closely reflects the way that science is done in the real world, where the analyst will choose query Q1, receive an answer A1, and then based on the answer A1, decide what the next query Q2 should be, and so on and so forth, choosing each subsequent query adaptively based on previous answers. Yeah, or perhaps there's a third possibility. And in this work, our goal will be to study exactly how changing the model of interaction from offline to adaptive or to something else can affect what tasks are feasible with differential privacy. Okay, so what's the motivation for our study? So there are a couple. So in theoretical computer science, it's a major research theme to sort of understand how models of computation, models of interaction can affect what algorithms can be designed. From a more practical point of view, the theory of differential privacy is filled with, amazing positive results, but is also shaped by important lower bound or negative results. And for the practice of differential privacy, it's important to understand exactly when these lower bounds hold and why, and in particular, possibly try to identify circumstances in which those lower bounds can be circumvented by perhaps changing the model. Another motivation for our work comes from this recent and beautiful connection between differentially private data analysis and generalization for interactive data analysis. And the connection is sort of as follows. If you start with a differentially private algorithm, then running that differentially private algorithm on a data set where the rows of the data set are thought of as a random sample from some population automatically guarantees generalization to the underlying population. And moreover, this connection holds even when the analysis that you do is adaptive, in the sense that an analyst is choosing their queries adaptively. Namely, a differentially private algorithm that remains differentially private when run on adaptively chosen queries ensures generalization in the adaptive setting as well. Sort of in cartoons, the way I like to think about this is that usually you think of privacy versus utility as some balance or trade-off, but the situation is more complex and interesting than that, and there are certain circumstances like this one where privacy and utility really reinforce each other. But this sort of raises a question, the driving force behind this improved utility for generalization comes from the fact that we've considered differentially private algorithms that handle adaptively chosen queries. But perhaps we've already lost something by requiring that our differentially private algorithms handle adaptively chosen queries. And it's worth identifying whether that's actually the case. All right. So before telling you about our work, I want to introduce some of the key notions that will go into the talk. The first is differential privacy, of course. You've seen the definition about 102 times now. So let's see. Yeah, now I'll give it again. Differential privacy, as you know, emerged from a long line of work in privacy-preserving data analysis in the computer science community. And the idea is that a randomized mechanism M will guarantee differential privacy if any individual should have only a small effect on the outcome of the analysis. And the way this is formalized is by asking us to consider experiments with the following form. So if you consider any pair of data sets, D and D prime, which are neighbors in the sense that D prime is obtained from D by replacing one individual's data and vice versa, that the mechanism M is differentially private if for all such neighboring pairs of data sets, the distribution of M of D is close in some sense to the distribution of M of D prime. Okay, and differential privacy, as you know, formalizes this with two quantitative parameters, epsilon and delta, relating the probability distributions with this inequality. The only thing I really want to point out is that for the purposes of this talk, we're going to consider epsilon to be fixed as some constant, 0.1. It's not going to matter for the talk. We'll think of delta as being substantially smaller, ideally cryptographically small, representing the probability, an upper bound on the probability of an extreme privacy catastrophe like leaking the whole data set into clear. For the purposes of this talk, 1 over polynomial in n suffices. Okay, so the next important actor is going to be the kinds of queries that we'll be interested in answering subject to differential privacy. And in this talk, we'll focus on counting queries, which simply ask, given some predicate Q, what fraction of the rows of a sensitive data set D satisfies some property Q. So for instance, I might, on this extremely important data set, ask some questions like what fraction of the Beatles played the drums, what fraction ended up being vegetarian, fraction are right-handed, what fraction actually wrote a song. And in this case, the wrote single attribute, we get 3 out of 4. Okay, now we won't be interested in just answering one counting query. Of course, we want to answer a sequence of k somehow interactively chosen counting queries. And we make a choice about what it means to be accurate for a large number of queries, and the choice is as follows. We say that a mechanism M is accurate from k counting queries chosen from Q if with high probability the maximum deviation of any answer that M provides to query Qi is 0.05. Okay? And the choice of constants here, again, is not going to really matter. Okay, so just to quickly remind you, what do we know about answering counting queries subject to differential privacy? So perhaps the simplest example is these attribute mean queries, where I have D binary attributes, and I'm interested in estimating the means of all of those attributes. So what if I just wanted to answer one query? It's like wrote single query. The natural thing to do is to add Laplace or Gaussian or whatever noise, scaled to standard deviation roughly 1 over n. And the intuition, as you know, is that the sensitivity of this query is 1 over n, since each individual can affect the value of the query by at most 1 over n. So you should add enough noise to cover up one individual's contribution, which is about 1 over n. Now, how about answering many queries? Well, we can again just add independent noise to every query. And it turns out that the noise has to scale according to roughly root d over n. So there's some economies of scale going on here. You might guess that you're supposed to add noise d over n, but it turns out root d over n suffices. And this could be seen through a number of means, for instance, the advanced composition theorem of Dork, Rothblum, and Vedon, or just by directly analyzing what happens when you add multivariate Gaussian noise to the answers. All right. Just to offer a little bit of interpretation about this, if we want non-trivial accuracy in the sense that I've described, getting answers that are all 0.05 to the questions, then I can answer roughly n squared queries in this manner. So number of queries k is going to be conflated with the number of attributes d that I'm interested in, and I can answer about n squared. Is that okay? All right. Of course, this idea of adding independent noise doesn't stop at attribute means. In particular, I can ask, any counting query and add Laplace noise of the order 1 over n, for instance, to each one, or scaled up noise in the case of answering multiple queries. So in particular, I can ask, any sequence of k queries, add noise scale to root k over n, and then obtain differential privacy. And the point I want to make here is that this mechanism, because of the robustness of differential privacy under even adaptive composition, allows you to answer k being roughly n squared adaptively chosen counting queries. Okay? And moreover, some very beautiful and important works showed that the buck doesn't stop at n squared query. In fact, with counted queries, one can answer many, many more than n squared, even adaptively chosen counting queries. And the way it works is an analyst will ask some question Q1, and then the mechanism will apply some sophisticated techniques from online learning to answer that in each subsequent query. And for our purposes, the best result from this line of work is this private multiplicative weights algorithm of Hart and Rothblum, which showed that if I'm answering queries on a d-dimensional data set, then it turns out that I can answer exponential in about n over root d adaptively chosen counting queries. And I want to point out that if the number of people in the data set n is substantially larger than root d, that this is actually exponentially many queries in the size of the data set. Okay, so just to summarize that briefly, I'm going to use the term upper bound to refer to positive results, like the ones I've described, positive algorithmic results. And what these results show is that in these two parameter regimes, where n is smaller than root d and where n is larger than root d, we have the following results. We can answer roughly n squared queries and exponential and n over root d queries, respectively, in these two regimes. Okay. Now, I've alluded to the importance of lower bounds in differential privacy, so I want to spend a little bit of time talking about those. So, the seminal work of Denur and Nassim, which actually predated and motivated most of the work on differential privacy, offered these so-called reconstruction attacks, which showed that that there's a limit of exponential and roughly n queries that one can answer subject to differential privacy. Okay? And since then, these attacks and these lower bound techniques have been strengthened to show that in the two cases, or the two parameter regimes that I've described, the algorithmic results are tight. So in particular, for the simple attribute mean queries that I discussed before, one can actually only answer order n squared queries. So the simple technique of adding independent noise is actually roughly optimal. And moreover, for the class of all marginal or conjunction queries, one can actually only answer about exponential and n over root d queries with differential privacy. And this was shown in joint work with Ullman and Badan. Okay, and I want to emphasize now how both of these results apply to some fixed set of queries. So the fixed set of attribute mean queries in the first case, and the fixed set of all conjunction queries in the second case. So in particular, these hold, even in this easier seeming offline model of differentially private query release. Okay, so just to summarize, the upper bounds, the positive algorithmic results, hold in the adaptive model and are matched by lower bounds for fixed sets of queries, and in particular in the offline model. Now, of course, any positive algorithmic result in the adaptive model is going to carry over to the offline model, and then any lower bound or negative result in the offline model will carry over to the adaptive model. So a reasonable question to ask is, these results hold for worst case chosen sets of queries Q, but perhaps these models are actually equivalent for every set of queries Q, and we'd like to investigate whether that's the case. Okay, now before telling you about our investigation of this question, I'd like to formally describe what models we consider in this work. Okay. So the first model we consider is going to be the offline model. These are all sort of exactly what you think they are. So in this model, there's some fixed large family of queries Q. An analyst is going to choose some small set of K queries from this larger set Q all at once. The analyst will give the queries to the mechanism M in a single batch and receive answers to all of those questions A1 through AK together. Okay? Now, there's also the adaptive model, which is, again, exactly what you think it is. So in each of rounds J running from 1 through K, an analyst is going to choose a query Qj, where the choice of Qj from Q possibly depends on the transcript of questions and answers that the analyst has already asked and received so far, Q1, A1 through Qj minus 1, AJ minus 1. And then the mechanism has to provide an answer AJ before it's allowed to see the next query, Qj plus 1. Okay? Now, as I might have foreshadowed before, it turns out to be useful to consider a third model of interaction, which we call the online non-adaptive model. And it's sort of a hybrid between the two models, in the sense that we tie the analyst's hands in the same sense as in the offline model, in that it has to choose all of its queries in advance. But we tie the mechanism's hands in the same way as in the adaptive model by forcing it to answer each query one at a time. Okay, so more formally, the analyst will once and for all choose K queries Q1 through Qk from Q. And then in each of round J running from 1 through K, the mechanism has to release an answer AJ before seeing Qj plus 1. And it turns out that this model will be useful for the fine-grained understanding that we're trying to develop. Okay, so what are our results? In one sentence, our results show that all three models are actually distinct. To explain this, we first show a separation between the offline and online models in the following sense. There's some family, Q sub-prefix, and we call prefix counting queries, with the property that in the offline model, it's possible to answer exponentially many queries chosen ahead of time from this family. But in the online non-adaptive model, it turns out that you can only answer order n squared queries, matching the attribute means result. We also show a separation between the online non-adaptive model and the fully adaptive model. We have this family that we call correlated vector queries, which I want to point out are not actually counting queries. But for this family of queries, it turns out that in the online non-adaptive model, you can again answer exponentially many queries, but in the adaptive model, you can only answer a constant number of queries. Yes, Marco?
Are they still linear queries?
No, they are not linear queries. Maybe we'll get to see what they are at the end of the talk, maybe. Okay, any other questions about the results? All right, so, yes?
Actually, in this one, I mean, perhaps I should wait until you show it, but why do you have an impossibility of the online? I mean, it's not... Can you repeat the question?
These are non-linear
question
queries?
out loud.
So the first set of queries, these are counting queries.
These are counting queries, so why, so the online for the...
Well, we'll have to see what the dimension is.
Yes, so the dimension...
Actually, the online has the dimension. Okay, go ahead.
Okay. Yeah,
Okay.
that's fine.
Well, let's see how far we get. Maybe we can take the discussion offline. Okay, so here's the intuition, at least in the cartoons, that I can only give talks in cartoon form, so see how this goes. Okay, so maybe you've all had this experience. You're like taking some introductory physics class, and you're given some crazy circuit diagram, and you're asked to like answer, what's the capacitance of this part of the circuit, what's the inductance of this part of the circuit, whatever. So you're sitting this exam, your colleague comes to the exam, armed to the teeth with knowledge about electromagnetism. So when he sees this the multiple choice test, he's able to just use his vast knowledge to power through the test one at a time, like in an online fashion, answering each question as it goes. On the other hand, maybe I show up to the test, I've been partying all night, I don't understand physics at all. So I just come to the test with the knowledge that V equals IR and a big cup of coffee. Okay, so if I were to apply the same strategy of answering the queries online one at a time, I'd be hosed because I just don't have the knowledge to answer each question independently. But what I can do is, well, because this is a multiple choice exam and all of the answers to the questions are correlated, I can start anywhere in the exam that I want using my limited knowledge, use the answer to that multiple choice question to infer something about the circuit, which will allow me to answer another question, and perhaps in this question I can use the question stem itself to answer another question, and so on and so forth. So the fact that I have this entire multiple choice exam in front of me, where the dimension of the answers, like the answers that are internally consistent, is much smaller than the space of all possible answers to the test, allows me an advantage, even though I'm much less powerful than John is. Okay, so yes, I want to try to tell you at least what the family of queries that we consider are. So the family of queries is going to be prefix queries. And it's going to be a family of queries of some dimension d, which we'll always take to be polynomial in n. And each prefix query is defined by a set of strings of length at most d. And it's going to be defined by a set of, again, at most d of these strings. So they're short strings and not too many of them in each set S. And we're going to say that the value of a counting query Q sub S is going to be 1 if and only if there's a string, a prefix y in S that's a prefix of the queried string X. Okay, so a quick example. Suppose we have the set of prefixes 0, 1, 0, 0, 0, 1, 1, 1, 0. And the data point 1, 0, 1, 0. The value of the query QS on X is going to be 1 because there's some prefix 1, 0 that is in fact a prefix of the string X. Okay, so I guess I can only get into the intuition of why this works. And we have to break for questions. So the intuition for the separation is the following. In the offline model, if I'm presented all of these queries in advance, then I can use this strong overlapping structure of all of the queries to get some dimensionality reduction. So in particular, the effective dimension of the data on the queries that I actually ask is much smaller than the maximum possible dimension d of all of the queries. And this allows me to use these sophisticated algorithms like private multiplicative weights, which have a dependence on the dimensionality in order to get better results. On the other hand, in the online model, where I'm not given where the mechanism M is not given all of these queries in advance, it's unable to do this kind of dimensionality reduction. And in fact, you can show that you can embed this attribute mean problem into the problem of answering these prefix queries in an online fashion. And that is what drives this quadratic lower bound on the number of queries that you can answer. Okay, so with that, let me just skip ahead to the concluding slide, or not. So our conclusion is that to answer many queries with differential privacy, it can help to make up your mind and decide what queries you want to ask in advance. Some interesting remaining open questions. In particular, the separation that we proved between online and adaptive queries holds for some weird family of search queries, which I didn't have time to tell you about, but they're not counting queries, not linear queries. It'd be very interesting to see whether a separation holds for counting queries. Also, these prefix queries and search queries that we consider are not really, they don't really correspond to natural computational tasks. With an eye toward the practice of differential privacy, it's very interesting to see whether these techniques can be leveraged for practical examples of queries. And we have some evidence in both directions for the class of one-dimensional threshold functions. Okay, thank you.
Are there any questions for Mark?
Yes?
I didn't understand how these are counting queries, actually. Can you explain again?
So I've defined for you, I can go back to the set of queries.
So there is an encoding there.
What's the question again? Can you say the question again?
You said that these prefix queries are counting queries.
Sorry.
No, okay, maybe I see it.
So I've only defined for you what the value of a prefix query is on one individual data point, and then they extend to the rest of the data set
Okay.
In a linear fashion.
Okay, my second part of the question is, do you know anything about the setting where also, I assume that here all the queries are have a uniform parameter, like uniform epsilon and delta. Do you know anything about when you can also choose the epsilon and delta?
I see. When you can choose the parameters adaptively.
There you go.
That's a good question. I don't know the answer. There is the work showing that the composition of differential privacy when the parameters can be adaptively chosen is different from the parameters of differential privacy when the parameters are statically chosen.
Mm-hmm.
But those are not dramatic separations, I don't think. They're not, they're in like the extra logarithmic factors that you get at the end. And I think that's inherent. So I think for all intents and purposes, those two models might be the same. But I don't know if that's the correct interpretation of their theorem.
Are there any other questions? Okay, I think just
Wait, I have a question.
Okay.
So what is the role of the dimension in this first result? Because that has to come in answering Moni's question.
Yes.
Can you
So
shout the question? Could you repeat the question when they're asking?
What's the role of the dimension?
Okay, thanks.
okay. So improving our negative result, the lower bound for online queries, we'll take the dimension to be order n squared.
Mm-hmm.
Okay, to be exactly what you want to prove the attribute mean lower bound. Now, when the dimension is, and that's going to actually be the dimension that you encounter when trying to answer these queries in an online setting.
Okay,
Now, in the offline setting, we do dimensionality reduction.
I get it.
So the effective dimension of the space of queries that you're asking on a data set, if that set of data of queries is fixed, is going to be like logarithmic in something like d times n. Okay, so that allows you to answer exponentially many queries.
Like in
But the offline algorithm itself is able to handle a dimension that that's substantially larger than n squared.
And the complexity of the offline is?
Bad. Private multiplicative weights, bad.
Did you separate computation within?
No, we didn't address computational complexity at all.
any other final questions before lunch? Okay, let's thank both our speakers again. Good talk.